Okay, good afternoon, ladies and gentlemen. A warm welcome from my side. My name is Uwe Sigloch, and I'm located in the headquarters of ebm-papst in Germany. And I will today present you the latest information about our new product ranges, centrifugal fans. And but before I come to the fans, I will introduce or say a few words about the company ebm-papst, and I will also tell you about what motivates us to go into innovative fans and why it's necessary to innovate and to be more efficient. Then I will go through the product range of our new ReadyPack fans, and also together with the use of the fans, the right installation. And I will explain a few special features of these centrifugal fans and the motors used in such fans. And I will give a short outlook what will be next in this field. So ebm-papst was founded almost 60 years ago in South Germany. This place is on the countryside. It's green around, and this somehow also prepared ebm-papst to be very close to nature. After, let's say, 40 years of growth, and we had some acquisitions of some small or fan companies, and then in 2003, the name ebm-papst was launched. And shortly after that, in 2009, we started our activities, especially in direction of green products. Therefore, we created the brand mark GreenTech. And 10 years later, 2019, we added another feature to efficiency. That is the feature intelligence. So our fans are more than air movers. They also have a certain intelligence, which I will explain later on. So ebm-papst is a 2.2 billion euro company with about 15,000 people globally. And we have, you can see on the map, Europe is our where it all started. So Europe is our strongest market, but we have also sales offices and subsidiaries all over the globe, and production sites in Americas and in Asia. So very often the question arises, what is a fan? That is, we are dealing also with, let's say, regulators, especially EU Commission. And there the question always arises, what is a fan? So for ebm-papst, a fan consists not only of the aerodynamic part, so the impeller. So we take care also about the motor and the drive. So for us, the fan is the air mover, which where you have to put in some electrical energy, and you get the air flow and pressure out of the fan. And as all these components are relevant to efficiency, we have to look into all of these components, because an efficient fan is only as good as the maximum as good as the weakest point. So the history of Europe, especially European market, but I think in other regions it's some kind similar. This is a graph showing the power consumption of 3 cubic meters second against 1,000 Pascal. And over the year, let's say in the 50s, 60s, 70s, AC technology was the main drive. There have been no inverters, no speed control. There were you change the pulley if you need another speed. So you had transmissions, but in the 90s, it started with direct drive, and the reason for that was that speed controllability was affordable. And this ebm-papst took as a starting point of introducing big EC motors, line-fed EC motors with integrated drive. And you can see that over the time, the power consumption reduced from the 7.5 kilowatt to 4.2 kilowatt. And this is maybe not the end. So what are the drivers for us, and I think for the whole industry, to create better fans? There are regulations. It could be regulations on the product. It could be regulation on the application, like here on the air handling unit side, for example. In Europe, we have a classification scheme, ABC, efficiency grades for air handling units. So our customers are asking for more efficient products. And the Commission, Europe, created a fan regulation. Here you can see the required fan static efficiency over the power, input power. And we are expecting the red line to be the limit for the next step, which will come up. It's expected in 2025. So at the moment, we have to be as high as minimum as the black line. But also here, the pressure comes to improve the products. And there's for sure the market asking for more efficiency, because we all know energy cost gets more costly, and operational expenditures are the main money you have to spend when using a fan. So buying a fan is not the cost. It's at the end, it's the operation cost, and that makes us think about more efficient fans. By the way, this life cycle cost calculation can be done with the software that we offer to our clients. I will tell you about this later on more. Okay, wire-to-air efficiency. So it starts with the aerodynamic part. So we have designed a newly shaped impeller. This impeller is compared to the predecessor, made out of composite material. So with doing it in such a way, you can create much more complicated designs. You can modify the flow path through the impeller in such a way that you have less turbulences, less changes in air velocity, and a smooth operation. And such turbulences always cause energy losses on one side, and also create noise. And with this kind of impeller, we reduced it to the minimum we could find, and we put this in an overall product. The product range covers diameters 280 up to 630. On our booth, which is here on the show, we have a demonstrator that shows you how the fan looks like. So we have two design versions, because we find in the market applications where it needs compactness. So we have a version where the motor is more or less inside the impeller. That makes, and in computer room air conditioners, in home ventilation applications. Space is limited, and we have, but this costs also a certain amount of efficiency. Therefore, we have taken out more of the impeller and created a so-called long version, and this one offers the best of efficiency because motor is not disturbing the airflow through the impeller. So comparing this new product with the predecessor, we did an improvement in the overall performance. So the blue lines indicate the old fan family. So it's a pressure development over the air volume. And the green curve, this is a new ReadyPack C. We call it ReadyPack C because of the composite impeller material. So you see that we increased the air performance in respect to flow and also mainly on pressure. So we can operate them in quite high RPM level. Efficiency level, this is the envelope of the static overall efficiency, wire to air efficiency over the fan airflow. And you see that the envelope shows also over the whole range an increase in efficiency by 3 to 5%. 3 to 5% points means at the end energy saving 7-8% compared to the old. And here, what I mentioned before, this curve again from the EU regulation, you can see that we are far above the minimum requirement, and this far above minimum requirement is the benefits to you as a customer, that we are offering a much better fan than legally required. Comparing our EC motors with AC motors, this happens quite often. There is international efficiency grade, which is not suitable for EC motors because EC motors are out of the scope. But anyway, we get compared in projects with these levels, and we can say that we are far above IE4 level. Even especially on the lower power side, we are above the IE5 levels, which are not yet in place, but their figures are available. So EC fans or EC motors, EC is a technology, electronically commutated motors, synchronous motors, permanent magnet motors, is all naming the same thing. By its nature, an EC motor is always more efficient than any AC motor, and there are several reasons for that. First of all, in the rotor we find permanent magnets, and permanent magnets create, let's say, in the rotor the magnetic field that is needed to make the motor rotate. In AC motors, this magnetic field has to be induced, and this costs energy. That's one point. And another point is the winding, the way of doing the winding. You can see on the left, you can see the so-called single tooth winding. You can see that the copper head, we call it. This is the this area on an AC motor. It's this area. You can see on AC motor it's much longer, and this amount of copper is not useful to create torque, but the current has to go through. So current through copper, everybody knows, resistance, losses. So it creates heat, generates heat, you have to get rid of. So therefore, here also we see some percentage, some points where the EC motor has an advantage. And last but not least, there's the EC motor. It's a synchronous motor. That means it's running synchronously with the mains speed. So 50 hertz, 4-pole means 1500 RPM. An AC motor rotates, depending on the power, something about 1400 RPM. And this creates also losses. This is something that is not generally available, to have motors with included, implemented drive system. So that makes the unit compact. It makes it easy to handle. So you don't need to do a connection between a VSD and the motor. You don't need to use shielded cables, which is required when you use an inverter. And it makes the product easy to use in the application. And on top, we have every motor fan combination is tested in our lab, every part number, and therefore it's optimized system. You don't need to adjust ramp up time or adjust the program, the maximum speed, etc. This is all done in factory. So it's a real plug and play, easy to use product compared to an inverter where you have to go through the manual and do some settings. Even though the electronic is inside it or in a part of the motor, it can be on site, can be replaced in case of damage. So this is also something that is remarkable. Then there's another point. When you have the fast switching elements like inverters, VSDs, drives like our commutation electronic, which is more or less the same functionality as a VFD. It gets, you create a voltage difference between the stator and the rotor. This is the physics behind, and this voltage can create a current through the bearings. And you may have made the experience already when you take a standard motor, AC, and use a standard VFD, put them together. It may happen that after a few months, the bearings fail. And this has to do with this current through the bearings. We overcome this problem by using isolated shaft. So the shaft to the bearing is isolated, and therefore no current can flow and no damage of the bearing can occur. So it's also a kind of efficiency when you can use the product, take it out of the box and fix it with a few screws to the unit. So we have created a plug and play, ready to use product, simple use, simple mounting. This can be also seen on our booth. So we went through the impeller, what makes the impeller. I mentioned the complex design of the flow path. We have the wavy cover plate. It's quite round, that creates a very even flow path. And as mentioned before, this creates less losses because the air velocity is quite evenly over the whole diameter. Then the motor is, as mentioned before, a high efficient EC motor, permanent magnet motor. We use, that is also remarkable, in all our motors, we don't use rare earth magnets. All of our magnets are ferrites. So ferrites are very simple and easy to reuse and not so and easy to produce, and to not as rare earth magnets where you have, let's say, chemical pollution. And we have the compact external rotor motor design, so the impeller can be mounted directly on the rotor. That's why we can create very compact units. And the electronics. So some of the features I mentioned already, but there's some others like integrated PI controller. We have locked rotor protection, so we have over voltage detection, phase failure detection, and we have in the motors above, starting from 4 kilowatt power, we have integrated a sensor to detect vibrations. And later on I will tell you a little bit more about this feature. So we have accessories. One main accessory is the flow grid. This is something that when you install such a fan in an environment where the suction area, you have limited space, you may create also turbulences, and these turbulences hit the passing impeller blade and create loud total noise. And with this kind of flow grid, these tolerances get, so to say, slightly sliced to small portions, and so the impact when hitting the impeller is far lower, and so the total noise is reduced. And something new, we have added where it's needed, a protection guard to this flow grid, and so you can have both. One is safety and the other one is reduction of noise. So thinking into the future, we designed these final products, ready packs, also in such a way that our transport volume gets reduced. So when we are shipping these fans we save also CO2, because more fans can fit into a container, and this helps also to get more sustainable. This is especially in Europe, we have initiatives doing evaluating CO2 consumption over the whole process, so to say, from cradle to cradle. And this is a small okay, airflow determination. in all centrifugal fans backward curved, also in some easily by a pressure tap, you can measure the differential pressure between air intake and inlet cone, and you can calculate with a simple formula the airflow. And this is quite accurate and helps to provide the right with some control devices, provide the right amount of air. Fan efficiency is one point. You can create the best fan in the world, but when you install the unit in a wrong way, it may happen that the overall system is not very efficient anymore. So there are a few hints from our side to prevent this. And one thing is that is inbuilt into the fan. So former impellers, we had this in, let's say, 5-7 years ago in a similar way. The air leaves the impeller more or less in the radial direction, as shown here with in the graph. Nowadays we created the impeller in such a way that we slightly give the air flow a shift to the diagonal direction, and this helps reduce here when the wall, very often you have two sides of the unit very close to the impeller. It helps to reduce losses here, and as you know, losses are pascals, and pascals have to be paid by. So another thing to take care of, the dimensioning, the positioning of the fan in the unit. So it's on the suction side, you should have a certain space available, and also on the pressure side, especially in the so-called plenum fans. The plug fans are plenum fans. They more or less create an higher overpressure in this area, and when you have a certain distance to flaps or heat exchangers or filters, these devices get good air distribution, and so the efficiency of these units can also be increased. So we have a certain performance with our fans, but sometimes we find applications in the market where you need more pressure, for example. So here is the range of the fan, and the dots are, let's say, projects that we got from a customer of us. So sometimes, as mentioned, you need higher pressure. What can you do? For that reason, we created a more powerful EC motor. This motor is a 24 kilowatt EC motor, means 24 kilowatt with integrated electronic. This is unique in the world, and it's also shown on our booth, and you can use it in axial fans and also in centrifugals, and we use it diameter 710, 800, where we now can create higher speed. Before we had the limit at 12 kilowatt, and the gray area here is what we add to these diameters. So you see that we can run up to 2,500 pascals. So in applications like make-up air handling units, in clean rooms, or in pharmaceutical environment, or also in ventilation units where you have long duct systems and dense filters, this product can be used. And here, same thing, we come with all the features you know from our, or what was explained before. We have also the integrated vibration sensor and high efficiency. This motor is has about 95% of efficiency. Good. Yes, such a fan can also be used in retrofit. And we took care about the dimension of the fan. So the fan was created quite short in a overall length is below 900 millimeters. So it should be possible to transport it via elevators or staircases. It doesn't need cranes. So this is also a topic that comes, that we see quite often when we talk about retrofit activities. This is a graph I've before, a little bit different. Here it's going down to starting at 120 watts. You see the gap between EC motor and IE5 level is quite big at the lower power input. It gets closer at the maximum, but anyway, EC technology, as mentioned before, offers always an efficiency benefit. Here a simple calculation about comparison, conventional fan, belt-driven. We have transmission losses of the belt drive. VSD we have from both sides. We have impeller efficiency of an older fan, 70%, of a ready pack, 75%, motor efficiency 95%, and a standard AC motor 85%. And when you go through this calculation by using 1 kilowatt hour cost 22 cents, Singapore dollar cent, and 4,000 hours operating time over the year, you get a saving of $5,000. That translates into 5.8 tons CO2 when you use 250 gram per kilowatt hour CO2. I think this is more or less the value what we find in Singapore. Good. High pressure we covered. What about high volume? So when you have applications where you need much more air, you can just multiply by operating the fans in parallel. So this shown here in an example of a data center. This can be done with axial fans on that side or with centrifugal fans in a so-called fan array or fan wall. And this keeps the overall efficiency. So the single fan, if it has 70%, all the fans together will also have 70%. We create such a product by using aluminum struts and mount our standard spider mount fan inside, and then these cubes can be stacked. And we offer also some sheet metal parts that are put in between the different fans just to fix it. And here you can see a retrofit installation by using this kind of design. So here another one. Very easy. So the fan itself is the separation between pressure side and suction side. Vibration sensor, which is included now in our ReadyPack range, starting from 4 kilowatt. It's a sensor on the PCB that measures the vibration, the vibration speed, vibration velocity in millimeters second. So here you can see, or how is it activated. So when operating the fan the first time, you switch it on and you ramp it up from 0 RPM to maximum RPM, and the fan runs through the whole area. And you know, every rotating system has certain natural frequencies where you have a peak. So in this case, before the test run, or this is what through the test run, the fan learns. So it learns that at 900 RPM, there's a peak which is above a certain level, and then we have it at 1200 again, and there's one here. So the system learns about that, and it fades out these areas in the future operation. That means, so the red curve is before this fading out process, and the green curve is afterwards. So you see, the fan will never operate in this critical area, and this at the end helps to increase the lifetime. And another thing that can be done with the system is when the fan gets unbalanced due to or something that sticks on the blade, if it runs up above a programmed level, you can program it level, it gives a signal to the control device or building management system or wherever. And another topic that is we find very often in data centers or in big setups, it's the limits of harmonic current. So this is also a topic that happens with EC motors, with VSDs. We find, let's say, in a standard EC fan and also in a standard AC VFD-driven fan, we see about a so-called total harmonic distortion on the current side of 35%, for example. And this needs, and this value indicates how much you have to over-dimension your wiring. And to get, in some installations, it's required to be below 5%. And to do that, you can use filters. And we have created an electronic where this filter is integrated. This electronic has a power of 4 kilowatt. And what we do here is we bring the current in line with the voltage, and we bring it also to a sinusoidal wave, not like this one, which is quite uneven. And if we get into that, we are below this required 5% of THDI value. As mentioned, this electronic can be fitted on all our motors, 4 kilowatt only at the moment, but this is quite helpful in applications where the requirement asks for that feature. Retrofit, fan grid, efficient air path. So it's the same that I mentioned before. This kind of plenum fans create a pressure evenly distributed in this plenum. And when there's a heat exchanger, the airflow through this heat exchanger is evenly distributed, and so the efficiency of this heat exchanger or filter is optimized. This is not the case when you have, for example, such a fan where you have a quite high air velocity out of the impeller. And this is similar to when you use, for example, an axial fan in such an application. Here you can see also the axial air velocity. You can see that in the area of the blades, you have a very high air velocity, and this is negative when it comes to air distribution, when it comes to downstream use of filters and heat exchangers. So maybe an axial fan is not always the best choice when it comes to changing from one fan retrofit to another. So accurate data, this is something that we can provide because we measure every fan, we measure at maximum speed with the whole setup. So with the original electronic, with the original motor, with the original impeller, and we measure maximum speed and 5 other speeds. Lower speeds in this area, and with this information we can interpolate and get for every duty point we get very accurate information about the power consumption, about the noise, and about the current and all the other measured data, and we can create graphs like this, and you can our fan can also, by using a certain intelligence, just measure the airflow with a pressure tap, which I explained before, and the speed. Together we can determine where the fan is operating. So in which duty point. Is it a duty point which is, let's say, outside of the recommended area on a poor efficiency level? So this is something when you need to monitor the performance of the unit, this can be done by using this information in addition with the sensor. The data get compared in our selection software, so you can be sure that you find the right product with the highest efficiency or the lowest noise. You can create a file, for example, 5 duty points over a certain period of time, and you get the right amount of the right fans on one side, and on other side you get an information about the operation cost of operation kilowatt hour needed. Good. This can be calculated and compared and added capex, opex, and then you get the life cycle costs. Good. What's next? Yes, we are down at 4.5, 4.2 kilowatt for a certain amount of air. Something that comes up soon is that we add another diffuser to these centrifugal impellers, and this brings us down or up in efficiency about 5% points. So we are then down at 4 kilowatt for this amount of air. On the let's say green intelligence side, we have created now sensors and additional tools that make the use of the fan more visible. One thing is knowing about the duty point, another thing is temperature of the motor, electronics, the current, RPM, the power consumption. All the data can be taken out of the fan and can be used for whatever purpose. And this can be worldwide connected. We have with our new company ebm-papst Neo, we can provide a worldwide connected cloud system and help to optimize the overall use of the unit. So I now at the end of my presentation, and if there are questions, I would be happy to answer them.